Hello, I am Professor S. Shankaran in the Department of Metallurgical and Materials Engineering.
Hello, welcome to this lecture again on fracture mechanics. We have been discussing the crack problems. In the last class, we looked at the concept of energy release rate, and then we also witnessed how nicely it explains the critical crack length and catastrophic failure in terms of stable crack growth and so on. Right. So we will now turn our attention to the crack tip stress and displacement fields. So in fracture mechanics, the crack problems are addressed by analytic functions. Okay, so just give you a brief idea about what is analytic functions. So what are analytic functions? Analytic functions have to have the following requirement. The derivatives of a function of a complex variable w is equal to f of z is defined by dw by dz, which is also w prime, is equal to f prime as a function of z is equal to limit delta z tends to 0 into f z plus delta z minus fc divided by delta z. So this is a derivative, okay, as a function of complex variable. It is defined like this. And for the derivatives to exist, no matter how delta z approaches 0, it is necessary that the limit of the coefficient be the same. So which is shown in this graph. So no matter how delta z approaches, so it could be of this function, or where delta x is equal to 0, delta z could be I delta y, or it could be this function, delta y is equal to 0, delta z is equal to delta x, or it could be a linear function which approaches 0, or it could be a non-linear, something like this. So that is what it means. No matter how delta z approaches 0, it is necessary that the limit of the coefficient be the same. This is what it is given. So the function w or f of z is equal to u as a function of xy plus iv to the function of xy. By definition, du by dz is equal to limit delta z tends to 0 times dw by dz. If delta z is real, delta y is equal to 0. If delta z is imaginary, delta x is equal to 0. Okay, so this is a property of an analytic function. So why we are looking at it? Because we are going to look at the stress function, which is also called analytic function. So that is how you should understand. So the analytic function, which when we define as a stress function, they should have these similar properties. That is what it is we are discussing. Okay. So delta z is real. In this case, what happens? We can just rewrite this differential form like this, where dw by dz is equal to limit delta x tends to 0. Then you can expand this, okay, the equation like this, where u into x plus delta xy plus iv x plus delta xy minus u into xy plus iv delta xy. So if you can just regroup them into all this I side and u side, then we can rewrite like this. Then this can be rewritten like this, where dw by dz is equal to dou u by dou x plus I dou v by dou x. That is what it is. If delta I is real. For the delta z is imaginary, then the expression can be rewritten like this. And then what you will see is the dw by dz is equal to 1 by I dou u by dou y plus dou v by dou y, which can be recast into dou v by dou y minus I dou u by dou y. So for the two case, we are seeing this. One is delta z is real, and in another case delta z is imaginary. So you can put it together like this: dou u by dou x is equal to dou v by dou y, or dou u by dou y is equal to minus dou v by dou x. So this particular type of compatibility equations are called famously called Cauchy-Riemann conditions. So for the analytic function, any analytic function, they should obey these conditions. Okay, that's why it's quite popular. If the derivative dw by dz is to exist, the following conditions are to be satisfied. So which is nothing but dou u by dou x is equal to dou v by dou y, and dou u by dou y is equal to minus dou v by dou x. So this is called Cauchy-Riemann condition, which you have to remember for defining any analytic function. These conditions have arisen from the consideration of only two of the infinitely many ways in which delta z can approach zero. This is again important point to note. Cauchy-Riemann's equations are not only necessary but also sufficient condition for the existence of the derivative of w. So in earlier case also we have looked at the necessary and sufficient condition for the stable crack growth, right? So similarly we have this Cauchy-Riemann condition is not only a necessary condition but also a sufficient condition for the derivative to exist. So we can keep this in mind. In another important point to note from the analytic functions, if w is f of z possesses a derivative at z is equal to z naught, and at every point in some neighborhood of z naught, then fz is said to be analytic at z naught, and z naught is called a regular point. So these are some of the basic definitions for analytic functions, just for given for the completion of the knowledge. If function f of z is not an analytic at z naught, but if every neighborhood of z naught contains points at which f of z is analytic, then z naught is called a singular point of f of z. A function analytic at every point of the region R, the function is analytic in R, or the function is a regular or holomorphic. These are all some of the definitions in the analytic functions, just to keep it to our knowledge. So now we will look at the what are the modes of loading. This we have already seen. So what you are seeing here is mode 1 loading, that is opening mode, and then we also know that mode 2 in plane mode for sliding mode, and then mode 3 is out of plane shear mode, that is also called tear mode. So for all three of them, K1, K2, K3 are the stress intensity factors, and the corresponding fracture toughness parameter is K1C, K2C, and K3C. So we are now going to look at the stress field for the mode 1 case, and we will see how fracture mechanics proceeds to derive this K1, that is stress intensity factor. So what is shown here is Westergaard's stress functions. Westergaard has given simple stress function, that is capital Z as a function of small z, for studying the crack problems, where capital Z as a function of small z is equal to real part of z plus imaginary part of I imaginary part of z, where small z is equal to x plus iy. See, this is how it is defined. So you should not get confused with the small z versus capital Z, which is a stress function itself. The relevant Airy's stress function could be constructed based on the stress functions proposed by him. Okay, so in the fracture problems, Airy stress functions are quite popular, and for solving this kind of crack problems, this Airy stress function is proposed. I did not get into the details of this, but this Airy stress function is one of the method by which this problem is being solved. Okay, so the derivatives and the integrals of z are defined like this. So dz by dz is equal to z prime, dc capital prime, d capital Z prime divided by dz is equal to z double prime, and z bar is equal to integral z bar dz, and z double bar is equal to integral z bar dz. So this is some of the basic definitions we are going to apply into the Airy stress function, and then we will see. So Airy stress function is a very general function, stress function, which is being used in the crack problems. I mean, it is from theory of elasticity. And the Westergaard stress function is a very specific stress function for this particular crack problems. Okay, so that we have to differentiate. So if you use the Cauchy-Riemann conditions in terms of z, so we can write it like this: a real part of z prime is equal to dou real part of z by dou x, which is equal to dou imaginary part of z by dou y, and an imaginary part of z prime is equal to minus dou real part of z by dou y, which is equal to dou imaginary part of z by dou x. So you can see that there is a slight difference, the flip here for the real part and then imaginary part. This you have to keep in mind. So why are we seeing that particular Cauchy-Riemann condition? Because Airy stress function has to obey a biharmonic equation, which you are going to see, and also has to obey this Cauchy-Riemann condition, because that is a necessary and sufficient condition to be considered as an analytic function. That is how you should understand that. And now we will see that the mode 1 stress field equations. So Airy stress function for this problem, that is the center of the crack, is referred to the origin. So what you are seeing here is an infinite plate subjected to biaxial loading. So you have to see this, the sigma is here as well as this side. So it is biaxial loading, and the Airy stress function considers the center of the crack is referred as the origin. So this is an origin, y and x, and then this is r theta. So this is referred in the polar coordinates r and theta. So this is an Airy stress function. Phi is equal to r z double bar plus y imaginary z bar. So this function is proposed or taken from the theory of elasticity. It has been arrived at by different means, sometimes by even an intuition, but this particular Airy stress function is being applied in this crack problem, and how this is going to give the solution, that is the point we have to see. So the stress function selected should satisfy the biharmonic equation. So this is something, a condition for, for the, if you have any arbitrary stress function, you have to check whether this, like for an to be called an analytic function, you have some conditions. So similarly, for this to be applied to the crack problem, then again to be called an analytic function, these are the conditions it has to obey, and then we will see. So this is called the biharmonic equation, that is del to the power 4 phi is equal to 0. So which is written like this: dou to the power 4 phi by dou x to the power 4 plus 2 dou to the power 4 phi by dou x square dou y square plus dou to the power 4 phi by dou y to the power 4 is equal to 0. This is equation. So dou phi by dou x can be written like this. Since we know how to write the differential form and the integral form of the Westergaard stress function, which is given, so we can write it like this: dou phi by dou x is equal to dou by dou x into real part of z double bar plus y dou by dou x imaginary part of z single bar. So which is after differentiation it becomes real part of z bar plus y imaginary part of z. Then you can write it again for the dou square phi by dou x square. You can differentiate this and then you will get real part of z plus y imaginary part of z prime. So this differential we have already seen. So based on that we will just write it. It is quite easy because it is all very simple and straightforward. We have already given the basic definition. So it is like this. So what you get as a final dou to the power 4 phi by dou x to the power 4 is real part of z double prime plus y imaginary part of z triple prime. So this is the final expression for this quantity. So like that you have to take the other quantities like dou phi by dou y, and then it will be like imaginary part of z bar plus imaginary part of z bar plus y real part of z. Then now you apply the Cauchy-Riemann condition, what we have seen. So then it can be rewritten like this after applying this. Then it becomes y real part of z. Dou square phi by dou y square can be written like this, and the final expression is real part of z minus y imaginary part of z prime. So we are trying to get all the quantities for the biharmonic equation. So now you substitute this and then obtain this the cube term, and which is minus 2 imaginary part of z prime minus y real part of z double prime. So this is a simple substitution and rearrangement you will get, and for this quantity you will get this. For dou to the power 4 phi by dou y to the power 4 is minus 2 real part of z double prime plus y imaginary part of z triple prime minus real part of z double prime. Now we can take this, and because we know this quantity dou phi by dou y square we know already, so we can substitute that and then we can get this quantity again. So which is nothing but real part of z double prime minus y imaginary part of z triple prime. So now we will take this Airy stress function and apply the biharmonic equation, and we are substituting this, and what we are finding is 0. So the Airy stress function proposed for this crack problem is valid. So that is how we are validating this Airy stress function. So it is satisfying the biharmonic equation, and then we will also see that the summary of this just for the clarity. So this is a function phi is equal to real part of z double bar and y imaginary part of z bar, and then it is the condition, and this is a coordinate for this. So this is a Airy stress function summary, whatever we have evaluated so far, just to give you the recap. So then you can just substitute this into biharmonic equation, which is equal to 0. So that is just for the clarity. So now this stress function also requires some boundary condition. Okay. So what is the boundary condition? First, let us look at the crack geometry, what is given here. So if you look at carefully, you can look at the animation. The crack is just opening. This is y and this is x, and the crack length is 2a. So now we are looking at undeformed condition, and then while deformed condition it opens up. So deformed configuration or undeformed configuration you are seeing. So the coordinate is x and y, and crack length is 2a, and these are the boundary conditions. What are the boundary conditions? the one important point you have to understand before we get into the boundary condition is the moment you see that crack is opening, then you have to realize that the crack surface is a free surface. The crack surface is free surface. You can see that. So then, if you think of that free surface, one is top and another is bottom, then we look at this conditions. For A, I mean for the x between minus A and plus A on y is equal to 0, because it is a free surface, y is equal to 0, then these two stress also will become 0. Sigma y becomes 0. Tau xy, that is in plane shear stress, is also becoming 0 because of the free surface. Okay, that is one condition. The second condition is when z small z it tends to infinity. That means it's a far field. It's a near field. This is a far field. Far field. What happens? Sigma x is equal to sigma y, which is nothing but sigma. Okay, so in a far field it becomes to equal to sigma, and where tau xy again is 0. So this is the second boundary condition it has to satisfy. And along y is equal to 0 for any x, tau xy again is equal to 0 due to symmetry. So this is see what we are looking at is when we say along y is equal to 0, still this condition is written keeping this mind as a straight line. Okay, so since it is a very small deformation, these are all assumptions. So the in plane shear stress again is equal to 0 due to symmetry. That is again you have to remember. So these are the boundary conditions. So we have to see whether these boundary conditions are met by this stress function proposed by the Westergaard. So we will see what is the Westergaard stress function. Capital Z is equal to sigma into small z divided by square root of z square minus a square. So this is a Westergaard stress function proposed for the crack problems. Okay, in fact, this stress function is going to remain for all sort of modes of failure, mode 1, mode 2, mode 3. We will see, at least we will completely see the derivation of at least for the mode 1. Then we can just mention how the second and third equations will look like. So now we'll try to verify these boundary conditions. So sigma y is equal to dou square phi by dou x square, and this is already we have seen, and tau xy is equal to minus dou square phi by dou x dou y, which is minus y times real part of z prime. So we will now take this the stress function given by Westergaard and then try to see whether the boundary conditions are met here. So what is the first boundary condition? We know that where x between minus a and plus a, what happens to this term? So this term becomes imaginary. So that means the real part of z becomes 0. Okay, for y is equal to 0 and minus and x can be in the interval of minus a and plus a. So this is the first condition, boundary condition. Then it becomes sigma y is equal to 0 and tau y is equal to minus y real part of z prime also is equal to 0. So this is the first boundary condition. And what is the second boundary condition? We have that is a far field where z is much higher than a. So then it becomes z. Okay, so it becomes z. So the z becomes a far field stress. Then what we have seen, the stress function is equal to simply sigma, which is a constant, a number. It's a constant. So the derivative of this number is a 0. That is z prime is equal to 0. So now we will see. We can apply these conditions to sigma x, which is equal to real part of z minus y, imaginary part of z prime is equal to sigma, and sigma y is equal to real part of z plus y, imaginary part of z prime is equal to sigma. Tau x is equal to tau xy is equal to 0. So this secondary all the second boundary condition also satisfied. Okay, that is what we are seeing. Now, what is the next step? The next step is we are origin shifting. So originally we looked at the crack length as a 2a. So it was the center of the crack is kept as the origin of the description, but Irwin later proposed to shift this to crack tip to consider that as a specific problem. So the origin is shifted from center to tip. So then the z is defined as z0 plus a. So what is z0? This is this distance, small distance, and this is really assumed to be very localized and very close to crack tip. That is an assumption. So when you assume that, then the Westergaard stress function can be recast like this. You just substitute z is equal to z0 plus a. Then, since we are talking about very near tip stress field, the equation is obtained by making the approximation. Z0 is far smaller than the k, very close to the crack tip. Then with that assumptions, what this equations becomes what? We will take only this form. Z is equal to sigma a divided by square root of 2a into z0. So only this z0 is coming here because of the approximation taken here. So this can be rewritten like this: sigma a divided by square root of a into z0 to the power minus half. And now defining k1 is equal to sigma into pi a. This is a definition given by Irwin and Irwin's collaborator Keyes. Okay, so it is named, the K is because of the name Keyes, but this is the proposed by Irwin. What is to be noted here is in the literature, K1 is also defined without pi. Okay, so since it is proposed by this Irwin, so it is kept like that, but even without pi, the meaning of K1 doesn't change. So that is information you have to remember. So if you write a sigma using this equation, then this equation can be recasted like this. And if you replace z0 with r comma theta, then this can be written like this: r e to the power I theta to the power minus half. So the Westergaard function z then becomes k1 divided by square root of 2 pi z0, and the derivative z prime is equal to minus k1 by 2 z0 into square root of 2 pi z0. So this is straightforward from this equation. And now we can look at the mathematical definition of stress intensity factor. If capital Z as a function of small z is the stress function of the problem defined with respect to the crack tip, then K is equal to limit Z0 tends to 0 square root of 2 pi Z0 into capital Z as a function of Z0. So this is a stress function given by the Westergaard. But what is now we are deciding is this function is very close to crack tip, very close to crack tip. That is what it is. So the stress intensity factor describes the strength very close to the crack tip. So the interrelationship of the stress and the crack length in the fracture behavior is nicely represented by K. Unlike the stress concentration factor, K has units of MPa square root meter, and the credit goes to Irwin for coining stress intensity factor, and since then the fracture mechanics took a giant leap forward. So this is very important point, because even though energy release rate gave quite a bit of confidence in dealing with this subject, but the after defining the stress intensity factor only, people are able to quantify the near stress field solutions. Okay, it's a near stress field solution one can obtain by uh, looking into stress intensity factor. That is the idea. So very near tip stress field equations for mode 1 in terms of Westergaard stress functions, and if the stress function phi is known, then the stress components could be determined from. So what you have to remember is we have to identify phi, which is given in the Airy stress function, that could be different for different crack problems or different fracture mechanics problems. Okay, but in this case, it is given by the Westergaard stress function, and then we are looking at it. That is how you have to remember. And also remember that this problem looked at the biaxial tension. So the Airy stress function is real part of z double prime plus y imaginary part was sorry, phi is equal to real part of z double dash plus y imaginary part of dash, where z is equal to k1 by square root of 2 pi z naught, where z naught is very small as compared to crack length. That means it is very close to crack tip. The solution is valid only to the very close to the crack tip. Now we can write this sigma x, sigma y, tau xy expression in terms of real part and imaginary part, what we have derived using this Airy stress function. So it takes this form. So this is the stress field near the crack tip is given by this form. So now what we can do, look at it, is we can now rewrite this near tip stress field using this Westergaard stress functions. Z is equal to k1 by square root of 2 pi z naught, and z naught can be replaced by r comma theta. Then it becomes like this. So what is written here is, so r comma I theta can be recasted like in terms of cos theta sin theta like this. Okay, so and z1 prime is minus k1 by 2 z naught times square root of 2 pi z naught, so which can be written like this. So what happens is, this is nothing but r to the power 3 by 2, so then this can become like this. Then the cos theta sin theta function takes this form. So you have now z and z1 prime, so we can now substitute this this value, z value and z1 value, I mean z1 prime value, into the stress field equation, and then you will get the complete form of stress intensity factor. So very near tip stress field equations in terms of r and theta is given by sigma x, sigma y, and tau xy is equal to k1 divided by square root of 2 pi r cos theta by 2 into 1 minus sin theta by 2 sin 3 theta by 2, and k1 by 2 pi r cos 2 theta again multiplied by this. This is for sigma y, 1 plus sin theta by 2 sin 3 theta by 2. But tau xy is equal to k1 square root of 2 pi r cos theta by 2 into sin theta by 2 cos 3 theta by 2. So I have not taken step by step to in substitution, which is very simple. In the interest of time, I have just skipped that step. Then if you substitute independently, then also you will be able to derive this. So what is the importance of this equation? The strength of all sigma x and sigma y and tau xy completely relies on all depend upon only this k1. That is why it is called stress intensity factor. So what happens if r tends to 0? if r tends to 0, then this becomes infinity. Okay, and this part, it takes care of the orientation. Okay, it takes care of the orientation, and this is the one which the magnitude of the k1 only dictate the strength of this parameters. So in the above equation, when r tends to 0, the stress field has the singularity of root r. So root r singularity is quite important in fracture mechanics. That means at this point, at one single point, r tends to 0, this values becomes infinity. That is why it is called root r singularity. Okay. So the practical utility of this equation for the evaluation of stress intensity factor in experimental mechanics is limited, as the region of its validity is very small. Though this expression gives a complete idea of the stress field around the crack tip, but the utility for in a practical aspects like experimental determination of the stress field is limited, and people have to do so many other modifications, okay, which is actually uh, uh, beyond the scope of my discussion here, but at least my intention was to show how this stress intensity factors are derived, at least for the mode 1. Even for a mode 2 and mode 3, the basic forms will not change. They will all be the same. All the basic forms, whatever we have seen, is not going to change. But I urge all of you to look at the Professor K. Ramesh's course in NPTEL, and you can continue or verify this other quantities like mode 1, mode 2 derivation, mode 3 derivation, everything. You can learn it from there if you are really interested in pursuing that. So I will stop here for the my discussion on stress intensity factor, and then we will continue to discuss the uh, other displacement fields, and then I'll go to the crack tip plasticity, plastic zone in the next lecture. Thank you.